This is our last video in the Newton's Laws unit, topic 21. And here's our objectives. Apply Newton's second law to solve for magnitude and direction of forces acting on objects, as well as the magnitude and direction of an object's acceleration. So we're on page 35. This is topic 21. So what we know so far, you don't have to write this down, but when an object feels an unbalanced force, it accelerates. That's Newton's second law. And no applied force exists independently. There's always a reaction force of equal size in opposite direction. That's Newton's third law. For every action force, there's an equal and opposite reaction force. So, let's put this down here. If a huge truck, like in the video that I hope you watched right before this, hits a small car, also like in the video, which one feels a greater force? Pause the video and answer. And the answer is, drumroll, C. They both feel the same force in opposite direction. So what we're going to look at today is, why does a small car get obliterated? It clearly experiences a bigger force than the huge truck. Or is it not so clear? Example number 1. So let's start with, let's start with a golf ball. 500 grams. And a golf club. Swinging at it really hard. We'll say the golf club is, it doesn't matter what the golf club is, but we do know that this ball is going to accelerate at 40 meters per second squared after contact. So boom. I want to know, what's the force of the ball on the club and direction? Well, I know that this force right here, F equals ma, 500 grams, 1, 2, 3, 0.5 times 40 Newton, meters per second squared, equals 20 newtons. I know this force is 20 newtons, and Newton's law tells me that for every action force, there is an equal but opposite direction reaction force. So the force ball back on the club and direction is 20 newtons left. Yay! Okay, let's step it up. What about the truck and the car? In the video, we had a gigantic truck. Wheels. Lots of wheels. And then we'll say the mass is 30,000 kilograms because it's got a big toe. Hits a normal car. Change the color. Wheels. And we'll say the force at impact equals 1,000 newtons. And we'll say this guy is 1,000 kilograms. Maybe that was a pretty big force. Let's call it 10,000. All right, what's the acceleration truck and acceleration car? First thing we know is that forces are equal and opposite. So this car, we'll do car first. F equals ma. 10,000 equals 1,000 times a. Force truck on car. So divide by 1,000. Divide by 1,000, and we have 10 meters per second squared to the left. So this guy has acceleration of 10 meters per second squared. He was going this way, and he just turned right back around at this rate. Now let's solve for the truck. F equals ma. Forces are equal, just in opposite direction. So this guy also feels 10,000 newtons. Equals 30,000 times A. Divide by 30,000, and we get 1 divided by 3, or 0.33 meters per second squared. That's tiny. It's barely anything at all. So it's not that it feels more force. It's that this one has such bigger mass that the force it feels hardly accelerates it. I mean, the truck hit a little bump, but this guy was just obliterated, not because of more force, but because of less mass. And as we talked about, ignore this for a second, mass is indirectly related to acceleration. So if mass goes up, acceleration goes down. That's why the truck doesn't feel anything. Back it up. Okay, solve for this one now. Your turn. Here's the answer. Same process. 2 people. They each feel 150 newtons. 75 kilograms. 150 equals 75 times A. 2 meters per second squared left. And this person feels the same, because they're the same mass, 2 meters per second squared on the right. So all we're doing is taking Newton's second law, adding action-reaction, and being able to predict the direction of the acceleration.